Welcome everybody to the afternoon session. We have a lineup of 3 keynote talks, and the first one on quantum simulation will be given by Emanuel Bloch from Munich. Emanuel, stage is yours.
Thanks a lot, Christiane, and welcome everybody. It's a great pleasure to give this opening talk for the afternoon session on the field of quantum simulation. So in the next 25 minutes or so, I'd like to give you a brief overview of quantum simulations, how it's connected to quantum computing, focus mostly on AMO type quantum simulations with atoms and ions, and then tell a little bit about the challenges and outlooks for the field. So my own research started in the context of quantum many-body systems, so the field of materials and chemistry, and of course we are hoping that in order to understand such systems, devices like quantum computers and quantum simulators can help us, but they will also, for sure, also help us build new sensors and metrological devices. So all this understanding of many-body quantum systems will, I think, lead to distinct advantages in those different fields of science and applications. So one problem that in the context of material science, for example, is a very famous one, is the model of the Hubbard, so-called Hubbard model, connected to the phenomena of high TC superconductivity. And without going into any details right now of the problem, I would say it's a good problem because it's one of those kinds of reference problems we need for these new machines, the quantum computers and quantum simulators, to test the performance on. If there's a promise to bring something to solve those problems, we need these reference problems, which we can try the machines on different platforms and see which one of these machines is actually doing better on a specific problem. And the Hubbard model is a very famous one in the context of strongly correlated electron physics, in the context of superconductivity, and it is one of those reference problems one wants to study and wants to look at. So basically what we try to do then is we very often know the microscopic rules, the laws of physics that govern the behavior of many of those particles in material science or chemistry, but we cannot predict the material properties. Or we would like to know, how do we have to change those rules to actually have to get specific desired material properties? And that's where quantum simulators and quantum computers promise to help, in parentheses, in some cases. I don't think they will help in all cases, but there's hope that they will actually help in some cases. Actually, very connected to that is the problem of optimization questions, where they can be efficiently mapped onto actually physics problems, spin problems. So when you try to find a ground state of such spin problems, you're trying to do something very similar, that you're trying to find the ground states of some other physical problem like the Hubbard model. The only difference is these spin problems are very artificial. They're not really very natural in a sense, but they can be encoded in the same language. And if you find the solution for those, you found an efficient solution for your specific optimization problem, for example, e-mobility charging stations. Now, this problem might be actually very difficult. There was a recent publication in Nature Physics that showed in order to achieve quantum advantages on general grounds in such contexts, we might be as difficult as reaching fault-tolerant quantum computing. But there's, of course, hope that for specific problems might earlier on show some quantum advantage on solving these systems. Okay. So, the problem, of course, in dealing with these systems is the exponentially large Hilbert space. But one has to be, of course, a bit careful when we talk about this. So imagine my screen being this entire configuration space, this exponentially growing configuration space in the system. And but when we look at typical physical ground states of a chemistry or material science problem, it actually only occupies a very small part of this entire configuration space. And we typically can find very efficient classical numerical solutions to encode that problem, to solve that problem. But very often we don't know what those solutions are. And this is also where quantum simulators and quantum computers can, of course, help us. They can also help in the context of, when you are looking at dynamical evolutions of the system, where you're really exploring the entire configuration space of the system. But even for these ground state problems, I think these quantum simulators and quantum computers can help in benchmarking and finding better kind of numerical approximation techniques that were not known before. So what are people studying these days? So here are a few systems that people are looking at: atoms, ions, superconducting systems, quantum dots. I think across the whole array of quantum systems that are studied today in the context of quantum computers. Also, people are looking at quantum simulation applications. So in a way, what we try to do, we try to take this tiny material on the left-hand side, make it large and big and highly controllable, so we can look into the system and study its behavior in very new ways that are not accessible to us in real material systems. So here would be kind of the protocol of how one goes forward in such a quantum simulation. So you start with a material, for example, that you want to study. You then need to find a theorist that maps this onto a rule set. This rule set in physics is called the Hamiltonian of the system. Then you need the quantum engineers to implement this rule set on their quantum machine, on their quantum simulator. Then there will be some time evolution. The system will evolve and you will measure the outcome of the simulator. And then by looking at this output and learning from this output, you can feed back to the real system, real material system, how to improve that. So in general, we are actually dealing with a situation which is very connected to adiabatic quantum computing, where you start with an initial state, initial Hamiltonian, you slowly change that to a final Hamiltonian and the final state of the system. And if you do the changes slow enough, you always remain in the ground state of the problem and thereby have found the solution of your final state Hamiltonian, your final state rule set, which could be your physics problem, your chemistry problem, or your optimization problem. The only difference is really that quantum simulation is a restricted form of this adiabatic quantum computer because it doesn't typically allow to control all degrees of freedom which are needed for a universal adiabatic quantum computer. So just to put this in context again, we have this analog way of doing the calculation by implementing the rule set. And then we have the digital way in a quantum computer where you have a few set of elementary gates that you try to concatenate to come up with the same evolution. And now it depends a little bit what situation you're in, where you should use, where it would be advantageous to use one or the other solution. And I'm talking specifically still about the regime where we don't have fault-tolerant error correction. Of course, if we have a fault-tolerant quantum computer, then of course the digital way would be advantageous. So the analog way can be advantageous if you can implement the rule set directly onto your system, but you are typically restricted in which kind of rule sets you can implement. So that's the limit. The digital system, of course, has the advantage that you can basically realize almost any rule set built up out of these elementary gate operations. The downside is, of course, that you might need a huge number of gates and qubits to actually achieve the same time evolution as for the analog device. Then there's another mode of operation. There's the so-called variational quantum simulation, where you actually close a feedback loop between a classical computer and only on the quantum device store a variational wave function of your quantum mechanical state that you want to find the ground state of. The nice thing here is that you can basically study Hamiltonians that you cannot naturally implement onto your system, so even go beyond this limitation that I mentioned before. So if you compare, the two approaches, analog versus digital, you want to know how are we making best use of the quantum resources that we have available to our systems. And in order to quantify this, we just did a model calculation together with Matthias Troyer and Rudberg and Peter Zoller for this kind of Hubbard problems, these electron problems, and compared it to a digital approach. And we take the Hubbard system, take a typical calibration errors that we have in these systems, and look what would the digital device look at that would have to emulate the same evolution on digital machine. And you can see that even though our gate count was much lower than before, you would still need about 1 million gates with an exceedingly high fidelity in those systems to achieve the same evolution in your system. So depending on what you can achieve in the lab, what quantum resources you have available, I think this example shows that it can be advantageous to run your system in the analog mode versus the digital mode, especially in this NISQ area of quantum computing and quantum simulation. If you look at the systems, actually it turns out that most of them are actually very connected. Almost on all platforms that are studied today, we find implementations of simulators and computers. As I mentioned already, universality is limited for the simulator, which can be true for the quantum computer. There are different kind of models one looks at and different size of systems one can study on those systems, with the quantum simulations having less stringent requirements very often, and so you can actually go to larger system sizes in these cases. So let me focus on a few examples to go from the abstract model to show you a little bit of what we can do with these systems and focus on the atoms and ions, which are prominently studied in the PASQUANS consortium, for example, in the context of the Quantum Flagship, a consortium that I'm actually a member of. So there, typically you're dealing with atoms, ions, or molecules where you want to control the interactions between them. And the interactions one has at hand for creating kind of entanglement in the system are collisional interactions, dipolar magnetic or electric interactions, or Rudberg dipole-dipole interactions, or, for example, cavity-mediated interactions when you place these systems into a cavity and have all-to-all interactions by the photons propagating back and forth in this cavity. So one thing one can study at that we've been quite prominently doing in Munich is to use these so-called optical lattices to mimic kind of material science behavior, where we project light patterns to mimic a crystal of light for the atoms. We load ultra-cold atoms in these crystals of light and use so-called quantum gas microscopes to study the behavior of these systems, of these atoms in these ultra-cold lattices, mimicking the behavior of electrons in a real solid. And you can not only observe these atoms with single site resolution, you can also control them by focusing laser beams onto these atoms. You can shape the potentials. You can make this rather programmable by projecting arbitrary light potentials onto the atoms. Here's an example of such a digital mirror device, which we shine laser beam on, and then out comes, for example, an exotic lattice structure, a structure of a quantum wire useful for transport, or kind of barriers here. So you have huge flexibility in the underlying potentials that you want to study here. So right now we can do this with system sizes of up to a few thousand atoms. So here's a picture of a cold so-called Mott insulating state with 2,500 atoms observed in this quantum gas microscope approach. So quite sizable systems, which we hope to extend also in the near future to fermionic systems, to be able to study fermionic Hubbard type systems of similar size in our labs. So this is how you can envisage this. We have this array of particles where we can focus individual laser beams on and control the spin states of these atoms in these systems. So let me come back to this Fermi-Hubbard model for a second and go to the heart of what you're trying to really learn there. So there were, in this phase diagram that you see of the Fermi-Hubbard model on the right-hand side, you see that for low temperatures, for the undoped phase, you get basically an antiferromagnetic phase. And when you dope the system with holes, you get these interesting phases, among them the so-called D-wave superconducting phase. So essentially, from a conceptual point of view, what you try to learn is how do holes moving in this antiferromagnetic and background environment interact with each other? And that's the fundamental big open question one tries to learn about. So these systems can be studied with these ultra-cold atom quantum simulators. Here's a paper from Markus Greiner in Harvard showing that you can reach this antiferromagnetic phase and start to explore actually now doping the system and see how these dopants behave with the antiferromagnetic background. In order to do that, what's actually nice that we've come up in the past years with new detection techniques which allow us actually to resolve the spin states in such a quantum simulator. Oops, let me go back, that was too fast. So we can basically take snapshots of the quantum simulation and tell you where's the spin up electron, where's the spin down electron, where's the hole, where's the doubly occupied site. So we get full information on the spin and density occupation of such a lattice. And if you come from quantum Monte Carlo, this is like running a quantum Monte Carlo simulation on your computer where you get individual snapshots. But of course, here it's not the classical machine, here's the quantum machine that's doing this calculation. And then you can really go back to these fundamental questions of looking at how a single hole interacts with this antiferromagnetic environment, a question that was already asked, about 30 years ago by three of these most well-known condensed matter physicists of our time, Charlie Kane, Patrick Lee, and Nick Reed. And what remained a Gedanken experiment at that time to learn about this behavior is now actually becoming reality, where we can really study this in the lab. And here's just some recent results showing you that when we dope such a system, we can really get to quantitative numbers on how it actually behaves, how it, for example, changes its behavior from a polaronic metal phase into a Fermi liquid phase. And we can quantify directly through different observables that I've written down here, how the microscopic properties of the system change from polaronic behavior to this Fermi liquid behavior upon doping the system, and tell you where actually this crossover is actually happening. So this is a specific example where quantum simulations are giving us new insight into this field of strongly correlating electron physics. So another beautiful example that has recently emerged in the field are these Rudberg atoms trapped in optical tweezers. Here a picture from Antoine Boiret's group in Paris, where you basically trap individual atoms in focused laser beams, and through excitation to so-called Rudberg states, you can make them interact and have gates running between them, or have an analog quantum simulation run between them. And the nice thing there is that because these tweezers are movable, you can actually move the atoms around to wherever you want and place them at different places and configure your system basically completely at will by positioning the atoms at your specified distances. So this is also allowed to study, for example, many-body physics, where people try to find the ground states of so-called Ising magnets. And now already this has been shown to be carried out successfully with up to 200 spins in very programmable geometries, and very good agreement with theory, with classical numerical simulations showing us that we can indeed find, to very good approximation, the ground states of these complex Ising models. And here's a nice example showing how digital and analog meet, actually. I told you we have these different modes of running the system, but these are, of course, not exclusive. So you can, of course, concatenate digital operations to build up a certain analog operation, and then interleave it with an analog operation of some other Hamiltonian that you've implemented to make use of both worlds. And here, Antoine's group has recently shown that you can build up almost arbitrary spin couplings in these systems by engineering such pulses that are shown onto the Rudberg atoms to engineer the couplings in a very, very defined way. Now, this has given rise to hope that these systems can actually help to solve real-world problems, for example, in the context of optimization questions, where you would place the atoms on a graph, on a disordered graph, basically corresponding to the spin model you're trying to find the ground state for. And then, as I showed before, finding the ground state for the Ising model here would lead us to finding the ground state of this disordered Ising model and help us, through the mapping to these optimization problems, solve the optimization problems in context. So that's ongoing, and I think this is a very interesting and exciting and a nice aspect of where this can have real world impact. The third example I just briefly want to show you is from Rainer Blatt's group in Innsbruck on ion crystals, where people are studying, for example, in 1D geometries, about 50 ions in such linear ion chains, and can study interactions between them and dynamical evolutions. And also look, for example, at transport properties of such ions, of such artificial spin chains of very long length, of up to now 50 ions, and study new transport phenomena that were previously not able to reveal with standard material in the standard material context. It also allows us to generate kind of new entanglement and large degrees of entanglement across this 50 ion chain through dynamical evolution of the system, and probe this and reveal this actually directly in the experiments. So let me go finally to just a few minutes spent on where I see actually applications beyond simulation and computing. And this is in the context of metrology. And we are, the best atomic clocks today are built by holding atoms in these optical lattices, which here is an example from Junier's group in Boulder, where the electron cloud oscillates within each lattice site. And we use these as oscillators and count the oscillations of this oscillators through a clock, the frequency comb, for example, and this allows us to make fantastic clocks. But it's already clear that I think in the next years, we're going to see how we can see improved clocks by making use of these quantum engineering techniques, quantum simulation techniques of, for example, trapping the atoms in these lattices, or engineering interactions between them in the tweezer context to really target, to prepare entangled many-body states that are highly suitable for a specific metrological application. So we can, through the control that we're developing, we can not only use this for, in the context of material sciences or chemistry, but I think we can also will be able to realize new entangled many-body states that are highly suitable for building better clocks. So in that context, I think this is something that we're going to see much more emerging in the next few years, how these two fields of metrology and sensing and this quantum simulation, quantum control are going to meet with each other. Okay, so let me just mention a few challenges ahead for the next years, and I put them going to put them up in questions in the end. So for the systems I've introduced you today, we have 3 classes of systems with 3 system sizes: ions with typically 50 ions in a chain, tweezer arrays with 100, 200 atoms in these tweezers. The cold atoms can scale up to about a few thousands, maybe a few tens of thousands of particles. And I think what we're going to see also in the next years is merging of the best of those worlds, bringing together the technology of the tweezers together with the lattices, learning from this sophisticated control that we have in ion traps, for example, and bringing that to the less well-controlled tweezer or ultra-cold atom systems to make advantage there, to make use of these new possibilities. And in fact, what goes hand in hand is that very often the underlying technologies, the underlying photonics technologies, laser technologies are very often exactly the same. So there's a lot of synergies that one can leverage in this context. So yeah, so these are the opportunities and challenges. And let me actually jump to the last slide to already maybe trigger a few of the questions and outlook. So where do I see the field going in the next 5, maybe 10 years? I already gave you a few indications where I personally see the biggest applications of quantum simulations in the context of many-body systems, material science, metrology, possibly also in optimization. The big challenge we will have to face for the systems I introduced is to speed up cycle times, improve preparation and detection fidelities. How can we actually get together with the fantastic photonics industry we have in Europe, these technological developments that we need to advance those platforms through high power laser sources, modular laser sources, new modulators and multiplexers, and a new cryo environment, which will be very crucial for example, for the Rudberg systems, or simple things as vacuum cell development, where I think very often we struggle to find the right supplier that is able to hand us the vacuum cell we're interested in. I think also this combination of analog digital will be a thing that will be much more explored in the years to come. For us, of course, important, as I said, we can only simulate what we can implement, so we can want to enhance programmability of these systems by different ways. So how can we enhance that by new potential shaping ways, by new interaction engineering possibilities? And how do we scale up to millions of particles? I think there's a pretty clear path, at least for the ultra-cold atoms, to a few tens of thousands of particles. But I think it's not yet clear how to do that for millions of systems, for millions of qubits, which you would need, of course, in the end to make this even more applicable and even more powerful than we have today in these systems. All right, Christiane, I think I'm done. Thanks so much. I hope I stayed in time.
Thanks, Emanuel. You stayed perfectly in time. Thank you very much for this super comprehensive and nice overview. So viewers, you can ask questions by typing them in the live Q&A button that you see on the right-hand side of the conference platform screen. And let me just start off with a question while people are taking advantage of that opportunity to Emanuel. So Emanuel, the ultra-cold atoms at the moment are the champions in terms of numbers of particles. What is the limiting factor in going further? I mean, you mentioned 10,000 should be easily or straightforward to do, millions will be more challenging, but what are the obstacles there?
Well, I think it's, in the end, simple things is how much optical power do we have available in our lasers, right? So right now, the way we think to scale to tens of thousands would be to use these monolithic cavities. I showed a photo of that, of a ULE cavity that recycles the power, enhances the power to make allows us to make large scale optical lattices in an inherently robust way, which we could essentially, and that's nice for the next talk, could send to space also, you know, if we want to take a clock to space. So these things will, I think, take us to tens of thousands of particles. Beyond that, again, it's a question of how much power you give me and how much power scaling you allow, and developing the right optical elements to handle that. I think that really is a technological thing that can be solved.
Okay, we have a question from Jörn Epping. What are your views on photonic integration?
That's super important. I didn't show a photo of our lab, but when I show a photo of our lab, you know that photonic integration is going to be a big theme, especially if we want to make everything modular and compact. And we want to go away from the Lego systems we have right now. So Lego in parentheses, you know, our optical tables with all the mirrors. We want to integrate this, want to have integrated photonic components, modulators, switches, all this photonic integration is going to play a very big role.
Okay, so there are no further questions at the moment. I'll be happy to take more questions to Emmanuel if they come up, but I think we can move to the next speaker already, even though we're slightly ahead of schedule. And that would be Ivo De Giovanni, and he's giving the keynote talk on quantum metrology. Ivo, stage is yours.
Thank you very much. Thank you very much, Christine. Can you show my presentation? Okay, so it's okay. It is not moving.
It's moving now. I think you're good.
Okay. So perfect. Thank you very much. I wish to thank Christine and the EQTC board for this kind invitation. My name is Ivo De Giovanni, and I'm a senior researcher in INRIM, and I'm the chair of the European Metrology Network for Quantum Technology. It's essentially, in my talk, it would be completely impossible for me to provide a complete overview of what is quantum metrology, because quantum metrology is really a huge field. So my idea was to give you some idea of what is quantum metrology. And the first thing that I noticed that the quantum metrology as a definition that is really community dependent. So for example, if you look at quantum optician, the quantum optician community perceive quantum metrology as quantum enhanced measurement. If you ask to metrologists, to the community of the National Metrological Institution, quantum metrology is something that is rather different. And there is also a third definition of quantum metrology as metrology supporting development of quantum technology. And I will make some paradigmatic example connected at least with quantum communication. Okay, so for example, let's start to quantum metrology as quantum enhanced measurement. Essentially, if we are speaking about photons, it is well known that measurements are limited by the precision of the measurement is limited by the shot noise limit. It is that the square root of n in the number of photons. It is affect all the optical measurement ranging from interferometry to lithography to imaging and so on and so forth. There is possibility to overcome such a limit. We have got a nice presentation this morning by Emanuel Bloch regarding this, but for example, also exploiting quantum optical state. For example, Fox state may be generated for example, from single photon sources rather than exploiting a correlation. So exploiting twin beam state have got a perfect correlation number of photons, and you can take advantage of this perfect correlation in the number of photons to reduce to go below the shot noise limit. This is, for example, the case of subshot noise imaging, and regarding subshot noise imaging, Euromet was able to develop a real working subshot noise microscope, but it can also be the case of quantum illumination, where even if the entanglement is already broken, anyway, the advantage of exploiting quantum light is still there with respect to the use of non-quantum light. If we move to another field, so for example, what is quantum metrology for the metrologist? Essentially, this is the new international system of units. You know, in November 2008, what's happened was that essentially the new international system of unit was developed, and this new international system of unit is no more related to material standards, such as, for example, the kilogram, etc., but they are defined in terms of fundamental constants. For example, the new kilogram is defined in terms of Planck constant. It has got measurement of this Planck constant through the Keeble balance rather than the Avogadro sphere. And then also the other quantities are somehow related to fundamental constants, such as, for example, the second, the ampere, that is defined through other quantum phenomena, such as the Geodesy effect, the quantum Hall effect on the single electron tunneling. Essentially, this is the Ohm law, completely quantum based, and the same happens also for the other units in the international system of units. And so essentially, for the metrologists, quantum metrology is this new system of units whose definition of the units are through the context and through phenomena that are, in most of the cases, quantum phenomena. But the third possible definition for quantum metrology is the one that I think is the more interesting for the quantum technologies community, that is the metrology that is supporting the development of the quantum technology. In particular, if I make the case of quantum communication, as you know, there is a huge standardization effort inside ETSI, but not only in ETSI, towards the development of standards for the quantum key distribution system. In this perspective, in this perspective, essentially, it is necessary to develop measurement that support such a standardization effort. This is essentially the aim of quantum radiometry and the activity towards quantum radiometry that are developed inside the Euromed framework. Starting from the end of the previous century, essentially there was a huge effort inside the European Metrological Institution to try to develop a linkage between the conventional measurement scale of optical radiation, or I would say something like a microwatt or milliwatt, to create a linkage to measurement at the single photon level. And in this case, essentially, not only this, so not only developing the traceability for measurement at single photon level, but also something more. So, for example, develop suitable metrics for single photon sources and single photon detectors, developing measurement for calibrating quantities that are outside the conventional metrology worlds, such as, for example, quantities that are typical of quantumness and so on and so forth. In this perspective, there were a huge number of projects, of metrological projects. Here there is a list of them, at least connected with the single photon metrology. Some of them were essentially aimed to develop novel standards and a novel traceability chain at single photon level, but there are also projects that are essentially connected to really to develop measurements that are of use for quantum communication. Just to make an example of the activities carried out inside this project. One example is developing a traceable technique for the measurement of the quantum efficiency of the detector. The idea behind that is very simple. What is done is making the substitution method, so calibrating the detectors, the single photon detectors, against a calibrated standard, a calibrated conventional detector through a calibrated attenuator. Then this calibrated detector, conventional detector, is calibrated, traceably calibrated to the primary standard. That is a cryogenic radiometer. That is a radiometer that is able to carry on an absolute power measurement. So power measurement, essentially, essentially, this is the primary standard, essentially. So the one that allows a direct measurement of the power of the emitting light. And then through that, the Metrological Institution have started comparison between the different institutes for detector, both at 850 nanometers, so in the visible, in the near infrared, and at the telecom wavelength, in order to prove that they are able to calibrate reliably their detector and to make a comparison between the results, the one with respect to the other. Together with this, there was also a first comparison on the measurement of G2 from single photon emitters, and this attracted attention also of Nature Physics, that wrote an article on that, showing that it was the first time that there was a comparison on a quantity that was really a quantity of quantum mechanical interest. So a quantity that is really purely related to the quantumness of the physical system investigated. Together with these, there are other relevant activities carried on in this sense. So, for example, investigation of weakness of the detectors. That can be a weakness for quantum key distribution applications. So, for example, information leakage, and we investigated the case of backflash emission. In particular, it was developed an OTDR operating at single photon level, and essentially what we learned from this measurement and having such a very sensitive instrument, that we were able to see what is the profile of the backflash emission of the detector. So essentially we saw that there is a backflash emission that can be an information leakage, and the shape of such a backflash emission can reveal what is the kind of detector is used inside a specific QKD system that can give extra information to a potential eavesdropper. And essentially the idea is this one. So essentially the eavesdropper just passively wait for the sign, for the backflash signal emitted from the detector, it can steal some information regarding which detector makes clicks or which kind of detector is inside the QKD system. And essentially, what is the probability of observing such a backflash from a potential eavesdropper? As you can see, changing the bias, the voltage bias of the detector, that we have investigated, what we see is that the probability of seeing such a backflash signal essentially increase, and this probability is absolutely not negligible. Another interesting application of metrology for QKD application that goes beyond to this idea of developing metrology for quantum technology is exploiting some metrological infrastructure for a different kind of application. And this is the case, for example, of the frequency distribution. So what is the idea behind that? The idea behind that is that the metrological institution, for example, you see here the Italian backbone, but there are essentially all the metrological institutes around Europe are developing such a backbone. Essentially, what there is in there is a frequency signal made from a ultra narrow, ultra stable laser that is used as a frequency reference and distributed around, are distributed towards user. Such a ultra stable, ultra narrow frequency reference that is sent through a laser signal can be exploited also for QKD application. The idea is exploiting such a signal for carry on twin field QKD. What is twin field QKD? Twin field QKD essentially take advantage of two phase-locked laser, and pulse from this phase-locked laser interferes in a central point that is Charlie, and essentially the results observed by Charlie, as in the case of measurement device-independent quantum key distribution, does not any information regarding which bit has been sent by Alice or Bob, but if Alice and Bob knows which detector in Charlie has made a click, they know what is the bit that is sent by the other, and in this way they are able to exchange a key substantially. What is the advantage of the twin field QKD? The real advantage of the twin field QKD with respect to the usual prepare and measure QKD is that essentially they allows you to avoid to use a trusted nodes in Charlie. And so what is really nice is that with the twin field QKD, you are able to make QKD communication at long distance, reducing by a factor 1/2 the numbers of trusted nodes that are necessary. And essentially, this is the trial experiment that we made in Italy, for example, but also there are also elsewhere where they are making this kind of application. And what is nice with our solution is that with respect to the other QKD approach, where they use often realignment frame to lock such a kind of big interferometers, essentially what is done here was that we used one of these ultra-stable lasers to lock the two laser in the Alice and Bob location, but also another laser line to stabilize the interferometer, so to correct the interferometric noise that will happen in the interferometer. And in this way, we are able to keep such a huge interferometer stable by much more than it was possible with just exploiting realignment frame. So to give you a bit idea of the result, this is what's happened in your interferometer, and the time scale, as you can see, are nanoseconds, are microseconds. And what you see there is essentially that you've got huge instability in your interferometers, while when you use our approach with the sensing laser that stabilizes interferometer, the interference remains pretty stable. To better understand, okay, this is just a schematic of the experiment of what we do. We make such an experiment between two places in Italy, and this separation is around 65 dB of attenuation. And what you can see here, this is our result. So essentially, what we estimate is that without such a sensing application, you have to essentially the fluctuation interferometer leads to a contribution of your Kubert that becomes relevant on the scale of hundreds of microseconds. While if you and this is the blue curve. While if you apply our this approach exploiting the the slide changed by themselves. So, but if you instead apply the our stabilization solution, what you get is that you have got a stability that goes up to few tenths of seconds. That is a clear advantage. So essentially, you need to apply realignment frame much less often, and that's essentially another possible added value that will provide the metrological infrastructure to QKD. All these things are developed under the premise of Euramet. Euramet is the regional metrology organization of Europe. Essentially, Euramet aims to promote the cooperation between national metrological institutions in Europe and to support the knowledge transfer. Furthermore, Euramet ran the European Metrology Research Program, under which premises are most of the project and the results that I showed you so far. And in this context, Euramet developed the European Metrology Network for Quantum Technologies, the EMQ. The main commitment of such a European Metrology Network is to become the unique contact point for stakeholders, industry, but also academia or research organizations that are interested in metrology for quantum technologies and want to collaborate with us in developing the required metrology that they need. Furthermore, another objective is supporting the standardization and certification of quantum technology, not only participating in such effort, but also developing the measurement infrastructure that is required to develop acceptable standard. Obviously, to promote the take-up of metrology and supporting the development of quantum-enhanced measurement that inside the metrological infrastructure that may help to improve the quality of the measurement carried out inside the National Metrological Institution. And finally, one of the main important result for the European Metrology Network for Quantum Technology is supporting the emerging industrial needs in terms of measurement in collaboration with the Quantum Flagship and the National Quantum Technology Programs. And with this, I was really a bit too fast, but I wish to thank all of you for your attention.
Thank you very much, Ivo, and for this nice presentation and for making my life as chair so easy that I don't have to chase any speakers. We do have a question from Osman Barish Malciolu, who is asking, what about dephasing and depolarizing channels? Can they be mitigated in a telecom fiber? And just, Ivo, before you answer, again, an information for those who have just logged on. If you have questions, please type them in the live Q&A slot, and I will read them to the speakers. So, Ivo.
Yes, they are, obviously, they are such a problem. Essentially, what is trying to carry on these the solution regarding TFQKD that we have developed is essentially taking advantage of such narrow laser whose bandwidth is really few hertz. In this way, you have got kind of long coherence time. So at the end of the day, and such a long coherence time anyway suffers noise inside the fiber, and so we never would be able to have such a interference pattern if we will not be able to compensate them, and essentially we actively compensate them with phase modulator in order to reduce the phase observing the phase noise and reducing such a phase noise with such a feedback control. This is essentially the idea regarding the phasing. And then yes, the polarization moves not that fast as the phase, but anyway it also changes, and so we also need to control the polarization. But this is a bit, I would say, this is a bit more easy because the time scale in which in such a huge interferometer the polarization change is anyway not that fast. So the life, I would say, is by far much more easier that the phase noise, the compensation of the phase noise, in which it is really the challenge to some extent. And this was really the biggest change that we are able to face and to overcome to some extent.
Okay, we have a question from Fernando Gago. Thank you for the talk. In your opinion, will quantum metrology be always restricted to the scientific world, or could it reach a more general industrial application in the future?
I think that quantum metrology and sensing will a quantum sensor will have really a huge impact in our life in the future. I would say they are already there. If I think to quantum clocks, the next generation of the clocks, they already have proven accuracy that is much better than the actual primary standard. And so for sure, soon the metrological community will redefine, for example, the seconds in order to take advantage of such novel improved technology. But I would say that in any field ranging from quantum sensor for electric, magnetic, and temperature that are based on color center rather than on hot atomic vapor, they will essentially overcome because they've got performance that goes beyond in terms of localized measurement of performance that are much better than the others. So I think that in the future there will be really a huge market for these, and these really will happen, I will say, soon.
Okay, so maybe let's leave it as this and not ask how soon will be soon. I think this may also become more clear, I think, throughout the conference. So thanks, Ivo. I take advantage of our session being super on time to still ask a question to Emanuel, the previous talk. Also by Osman Barish Malciolu, and he's asking how much can you scale? And that refers to the quantum simulators. Emanuel.
Yeah, thanks, Christiane. And thanks for the question. Yeah, as I mentioned, this depends, of course, a little bit which platform you're looking at. I think for the tweezers and lattice systems with ultra-cold atoms, we will see, we already have a few thousand particle systems in the lab, and I think we're going to see a few tens of thousands in the next 2 to 3 years. Beyond that, I think new technologies will need to be developed. For the ion systems, ion trap systems, I think there's the challenge how to go from 1D to 2D. That's the big challenge there. People are developing surface traps, for example, or shuttling techniques. So that's a little bit harder for me to say, but I think that's the path ahead. And as I mentioned to Christiane, I think most of this is for the light field trapped atoms, mostly technology limited and on the photonic side. So I think that this can be done. So it's not a fundamental obstacle.
Okay, thanks, Emmanuel. Thanks, Ivo. So we are ready to go to the final talk in this presentation that will be given by Albert Rurer, and he will give the keynote on quantum technologies in space. Albert, stage is yours.
Thank you, Christiane. So let me share my screen. Just a second. Hopefully you can see it right. So can you see the slides properly, Christiane?
See, I can see the slides properly, yes.
Okay, thank you very much. And thank you also for the introduction. So I'm going to talk about quantum technologies in space. And in fact, combining the great potential of quantum technologies with space offers plenty of opportunities for the development of disrupting technologies. And having recognized these promising prospects, the German Aerospace Center, DLR for short, has recently established 3 new institutes that are directly related to quantum technologies. I myself am leading a research group at the Institute of Quantum Technologies located in Ulm. Now, some of the main appealing features of space in this context are the possibility of achieving global coverage, establishing intercontinental links. Microgravity conditions in many cases can also be particularly beneficial, and also the fact that one has, compared to ground, a gravitationally quiet environment. Now, there are, synergies between fundamental physics and practical applications are particularly important in this field, namely the fact that fundamental physics always trying to implement, to test various principles and measure very small effects, always pushes the sensitivities, the required sensitivities of measuring devices. And that fosters the development of more and more precise measurement devices and hence of quantum sensors. But it's mutually beneficial in the sense that also the development of quantum sensors, making them sensitive, robust, more compact, is something from which future measurements and future experiments in fundamental physics can benefit from. So in the rest of the talk, these points will be illustrated for the main 4 areas of quantum technologies in space, namely quantum communication, time and frequency distribution, quantum sensing, and Earth observation. About quantum communication, Eleni Diamanti gave already a very nice talk this morning. And since time is limited, I'm just going to emphasize here that the Chinese mission satellite already demonstrated quantum key distribution, intercontinental quantum key distribution. And a key point here is the fact that compared to transfer of quantum states on ground with optical fibers, which is limited to tens of kilometers unless one uses quantum repeaters, free space optical links, which are available when link through a satellite is employed, don't have that limit and allow, as I said, establishing intercontinental distribution of quantum keys. and also global coverage without the need of having deployed a wide network of optical fibers with quantum repeaters. Now that's for more practical applications, but just as an example of applications to fundamental physics, I'll just mention this mission proposal. This is a NASA mission proposal, but also with participation of DLR. It's about deep space quantum links. So it has several phases where quantum links to spacecrafts on low Earth and middle Earth orbit are initially established, and eventually getting all the way to links to the lunar gateway that will be orbiting the moon in the future. This would allow to test, perform belt tests at scales where even human decision can be employed, and also quantum teleportation for these long baselines, to demonstrate quantum teleportation for these long baselines. And overall, this can be exploited to test quantum field theory in curved space-time. Another example of measurement would be measuring gravitational redshift, a general relativistic effect, using interferometers, optical interferometers with no classical analog, for example, based on two-photon interference with frequency entangled photons. The second area is time and frequency distribution. And here, this can be naturally exploited for clock comparisons in the context of metrology, but also fundamental physics applications. The interest of, so we heard already in Ivo's talk about networks based on optical fibers to do precisely that. However, the interest here is that, again, this would allow intercontinental comparisons and also global coverage, which has particularly interesting applications, as I'll mention in a moment in my next slide, on the so-called chronometric geodesy. Also, in the long term, it can also be interesting to actually have very stable and precise master clock in space, rather as a frequency reference and a time reference, rather than having them on ground and then referring to that from ground. A key effect, a general relativistic effect that will play an important role in the discussion I'll have in the next slide, is the gravitational redshift. And the basic idea here is that if we have two clocks at different heights in a gravitational field, they will tick at slightly different rates. And this is given by this formula relating the slightly difference in proper times or frequencies to the difference in the gravitational potential between those 2 points where the clocks are located. This is, one can perform measurements like that of this effect to test, for example, the equivalence principle, which is a basic principle, a cornerstone of general relativity. It's an effect that is already taken into account, is relevant when in normal operation of global navigation satellite systems. And it's also something that can be exploited itself, as I was saying in the example I'll mention now of chronometric or relativistic geodesy. The idea here, as I said, is to exploit the gravitational redshift that was related, as we saw on the previous slide, to differences of the gravitational potential. And the idea is to use these small differences and the fact that nowadays we have very, very precise atomic clocks based on optical transitions to determine equipotential surfaces and hence to determine differences in height with a precision better than 1 centimeter if one has, with the resolution that is already achievable nowadays with some of the best optical atomic clocks, or even better resolution in height in the future. And the basic idea is, as I said, exploit the gravitational redshift, and then what is needed is actually the comparison between a reference clock at some fixed location, could be a metrological institute, and then some transportable clock that one can take to whatever point one wants to measure what the height of that point is. And then the idea is that in principle, one could connect those clocks, of course, with some optical fiber network, but in general, if you want to have global coverage and take your transportable clock to wherever you wish, one can take advantage of the satellite links, optical links through a satellite. And you see here on this slide on the left, the comparison of the methods that are traditionally used in geodesy for this, which have some limitations in terms of coverage and also precision for some regions, and how this can be in principle almost straightforwardly done when one has transportable atomic clocks which reach this kind of precision and stability. Just here, two examples of already planned space missions implementing some of these ideas of atomic clocks in space, and also microwave and optical links between different clocks on ground. One of them is ACES. This is a European mission of the European Space Agency, and the key ingredient here is an atomic clock, an atomic microwave clock, same as employed in the nowadays in the frequency standards in metrological institutes, with cold atomic cesium. And as I said, it would also be equipped with the possibility of having microwave and optical links to ground. The expected launch, this is already very advanced, has been, you know, in construction, design and construction for a number of decades, but it's there were some slight delays, but it's expected to be launched, if everything goes well, next year. Another example is a proposed NASA mission. This is more ambitious. It's more, well, both of them, also ACES, the idea is to perform tests of the gravitational redshift and tests of general relativity. This NASA mission focused, the idea is to perform that with even higher precision. ACES would be located on the International Space Station, so about 400 kilometers above us, whereas FOCUS is aiming at having this elliptical orbit, highly elliptical orbit with a much, much larger apogee, which allows you to actually have a larger gravitational redshift signal, and also using even more precise atomic clocks based in this case on optical transitions rather than microwave ones like ACES. It would also incorporate two-way optical link. And as I said, this is for a longer time frame compared to ACES. Now moving to quantum sensing. So in this case, I would like to focus in particular, since Ivo also mentioned a little bit, some examples of that, on atom interferometers. And first try to explain briefly here what is the basic idea of the use of atom interferometers for acceleration measurements as inertial sensors, in particular here as accelerometers. So in this slide, on the left, this diagram, everything is happening here really in one dimension along the vertical direction. So the motion of the atoms along the vertical direction, the main laser beams that will participate in the interferometry are also along the vertical direction. And then you see the evolution depicted on the diagram on the right, this space-time diagram, which is where the central trajectories of the atomic wave packet are displayed in blue and green. And then you see these short light pulses that are 3 short light pulses that are applied at different times. And they give rise to light gratings that diffract the atomic wave packet so that they are split in the first laser pulse, then redirected by the second laser pulse, and finally recombine and then read out at the 2 exit ports. So the idea here is that the atoms in general will accumulate some different phases along the 2 arms of the interferometer, and this phase shift, which will in general accumulate some interesting, will depend on some interesting information of revealing the different evolution of the atoms along the 2 interferometer arms. This phase shift can be read out from the interference signal, which in the simplest case would correspond to measuring the number of atoms detected in one exit port and the other, and then just plotting, looking at the fraction of atoms at each exit port. That's something that will oscillate as a function of the phase shift. Now, in particular, the atomic wave packets acquire some phase when diffracted by each one of these three laser light gratings, which depends on the relative position of the atomic wave packet, its central position, and the wavefronts of this light grating. So in this way, by considering, the full evolution with the 3 light gratings, it turns out that these phases, they add up to a contribution that basically depends on the relative acceleration between your atomic wave packets and the reference of the wavefronts of your light gratings corresponding to the laser pulses. So in this way, you can measure gravitational acceleration, for example, or in general, accelerations of the atoms that act as an inertial reference. They are freely evolving, freely falling between the laser pulses. So you can measure accelerations between the atoms as inertial references and the wavefronts of the light grating. This can be applied. This has been already, this has demonstrated a great potential already in a number of very precise measurements in fundamental physics. This was the main driver for a number of years, but it's become already mature enough to start to be used in more practical applications already. You have a list on the left of various examples from geophysics to search for natural resources, but also civil engineering, where you can do underground surveys, just detecting what's happening, processes or structures underground, just based on the gravitational effect that you can measure on the surface. And there are, in fact, already a number of spin-off companies that are already, some of them for a number of years, that are already commercializing such kind of quantum sensors based on atom interferometry. An example is Muquans from France, but there are others also, AOSense in the US. And then there are other bigger companies that are already have some departments, some teams that inside that are also developing these kind of products based on atom interferometry for practical applications. So here I wanted actually then to go back to fundamental physics and measure a few important examples of the kind of fundamental physics measurements that have been done with atom interferometry. The first one is measurements of Newton's gravitational constant, big G, which is, by the way, the least accurately determined fundamental constant of all by several orders of magnitude. And all other measurements so far basically are based on the same principle and very similar devices, very similar to the very first ones, the first experiments done by Cavendish, several centuries ago. So in this respect, having a different approach, the very different system with very different kind of systematics, and with the possibility for actually substantial improvements in sensitivity in the future is very interesting. The other two examples are based on or correspond to test of the equivalence principle. As I mentioned earlier, is a cornerstone of general relativity. And in this particular case, these two measurements are based on precise measurements of accelerations of different atomic species simultaneously, and looking at the difference between the two to test whether both of them, as predicted by the equivalence principle, or according to the equivalence principle, whether both of them fall with exactly the same acceleration in a gravitational field. And the more recent experiments comparing different isotopes of rubidium have reached already, have tested this universality of free fall at the level of 10 to minus 12. Now, these recent improvements in this test of universality of free fall that just in about half a decade imply an improvement of about 5 orders of magnitude compared to these earlier measurements and other similar ones. There have been several elements, but there is one which is also an important point, which is also relevant for planned improvements in measurements of the gravitational constant, G, in the future, and it has to do actually with gravitational gradients. So what I described on my previous slide, the explanation was based on the idea that one has uniform gravitational fields, but in reality there are small modifications with respect to small deviations with respect to a uniform gravitational field. And these lead to actually very small effects, but for these very precise measurements, they become actually one of the major systematic effects due to dependence of your interference signal on the very high sensitivity to the initial position and velocity of your atomic wave packet, much more than what you can precisely determine. So that's a big challenge, but unfortunately there has been recently a very effective technique to overcome this problem. So you see here, this Einstein elevator here, you see that when you have deviations from the ideal situation of a uniform, perfectly uniform gravitational field, in the freely falling frame, you have some tidal effects due to these gravity gradients. These are very small effects that lead to small, instead of straight lines for the trajectories of your atomic wave packets, that they get slightly curved. This is a small effect, but as I said, when you do very precise measurements, this turns out to be an important source of loss of sensitivity and of systematic effects. But this can actually be overcome by using a technique that is based on a suitably adjusting the laser frequencies of the central pulses. And so this has already been demonstrated, for example, in the third experiment on test of the equivalence principle that I was mentioning before. So besides that, in space, one can combine this technique with the idea of the so-called orbital demodulation, which is based on the fact that the signal of interest here, the gravitational attraction, so this would correspond to the orange arrows, and other spurious effects like due to gravity gradients here would correspond to the blue arrow. They are modulated by a different multiple of the orbital frequency. And so by using some demodulation techniques, one can actually separate them. This is a technique that has already been employed in space with macroscopic test masses, measurements with macroscopic test masses, but it can be combined with the technique I mentioned before for atom interferometry to achieve even higher sensitivities with this kind of atom interferometry experiments in space. So I'm mentioning this idea of having atom interferometry experiments in space. Of course, before that, maybe it's interesting to mention or to summarize again the advantages of space specifically for atom interferometry measurements. And one of them, this is a case where microgravity conditions play an important role because they allow for long free evolution times. Between laser pulses, the atoms are freely evolving, they are freely falling. And so the fact that you are just basically in a freely falling frame here in your spacecraft, this allows for long free evolution times between and that increases the sensitivity. Remember that it was quadratic with time. Also, the fact that you have a gravitationally quiet environment is very beneficial for this kind of experiments, and particularly for fundamental physics measurements and tests is also very interesting to have the possibility of accessing large variations of the gravitational potential and velocity. And finally, as I mentioned on the previous slide, you can combine that also with interesting modulation techniques in space. Now, having atom interferometry experiments in space, so it's very interesting. They have these very appealing features, but of course, these kind of experiments in space require very substantial development efforts to reach the technological readiness level that is necessary for such experiments in space. Nevertheless, you can see here already very, very important steps and progress in that direction. So you have several reports on several experiments. The first one was with a sounding rocket, more than 6 minutes, and reaching nearly 300 kilometer height. So these were actually the first experiments where the first BECs in space and matter wave interferometry experiments in space were achieved about 4 years ago. The second one is the Coal Atom Lab. This was, by the way, a German project funded by DLR also in a collaboration involving a number of German groups in German universities and research institutes. The second one is some measurements. So the first also a BEC created in space, in this case, a device, the Coal Atom Lab in the International Space Station. This is something that is operating, continues to operate there. And for example, atom interferometry experiments are being routinely performed there, and our group is also involved in those. Finally, the third example is a proposal for a next generation device similar to the Coal Atom Lab, but learning on the experience from the quantum, the German Quantus and Myers projects and the American Cold Atom Lab to actually implement a device with many more capabilities and much better specifications. So this is something that is planned in the, within this decade to be launched to the International Space Station and to perform a number of interesting experiments. But of course, to achieve these results and, for future developments, as I said, it's very challenging to prepare all these things and to get the required technology development for such platforms in space. And the key role for that is actually the preparation using ground-based microgravity platforms. And I'm illustrating that here with two particularly relevant ones. One is this drop tower in Bremen, where one can either drop a capsule or launch it from the bottom, and that gives you, I wrote 4, but it's almost 5 seconds of free fall time, of microgravity time when you drop it from the top, or nearly 10 seconds when you launch it from the bottom. This has only a limited number of drops that you can have per day, and that's one of the main limitations. Interestingly, there is also now another facility, the so-called Einstein elevator in Hanover, where one can achieve fairly long microgravity times as well of 4 seconds, and many more drops or launches are possible every day of the order of 300, up to 300. But still, having lots of statistics, because these also will need to be shared with other experiments employing this facility, and also if you want to have very good control of your systematics and so on, it's actually also interesting to have prototypes that are dedicated for very high precision measurements to really demonstrate that you can reach that level of high precision with atom interferometry in relatively long times, maybe not as long as those that you plan for experiments in space, but still of the order of more than 2.5 seconds or so. And in order to achieve that, one needs to use these 10-meter atomic fountains. The one on the left in Stanford, it has already delivered a lot of very interesting results in fundamental physics, but there are others in China, and also the one depicted in the middle, which is being commissioned in Germany, in Hanover. And just as an example of, so here just compared to the microgravity platforms where you have a relatively compact, in this case, capsule that is launched or dropped and all your equipment is inside that. In this case, your atoms are, the whole device is in the laboratory frame, but the atoms are launched inside this 10-meter vacuum tube. And just examples of the experiments that can be performed there. So a test of the equivalence, test of general relativity in the quantum regime. So here one would be comparing not two independent clocks as on previous measurements of the gravitational redshift, but actually consider a single clock in a quantum superposition at 2 different heights, and then measure the gravitational redshift by looking at the interference signal. This is something that could be implemented with some slight variations already in this atomic fountain in Hanover, and there are even more ambitious facilities. This one exploits a 100-meter deep shaft from a previous particle physics experiments at Fermilab, and it would it's already under commissioning, and it would actually allow to search for ultralight scalar dark matter, and also a prototype of gravitational wave detection that, if demonstrated to work successfully, could in the longer term lead to a full-scale space mission for that. And finally, just very quickly about Earth observation, just to give you an example of the kind of measurements that can be performed, very relevant, for example, for climate change, to monitor changes of ice shelves, or in this example displayed here, this is actually monitoring the groundwater aquifers from space through gravitational measurements, and to see whether they are being replenished or they are being stressed. And the color code here corresponds to changes of 1 millimeter per year of the level of this groundwater. So just maybe so we have time for questions. I thank you very much for your attention, and leave it here with the summary.
Thank you very much, Albert. Also, thank you for staying on time. And And I should switch on my video. We do have already one interesting question, again by Osman Maciolo, and he's asking, how far are you from implementing LIGO in space?
Well, I mean, that is LISA. So LISA would be the next gravitational wave detector in space, which would be very sensitive to a very interesting regime of lower frequencies. And that is, again, an impressive and, very, very ambitious kind of mission with 3 satellites. But LIGO was also very ambitious, and it's really remarkable the sensitivities that have been achieved. And actually, one of the key elements of LISA is having this drag-free control of you, because you need to have your test masses that are perfectly freely falling and not disturbed by any external forces. But then you also want to make sure that your satellite surrounding these test masses is also not disturbing that a lot. And one needs to have an excellent drag-free control despite external perturbations of these satellites. That seemed the most demanding, maybe, requirement on LISA. But actually, there was this Pathfinder mission that was launched a few years ago to demonstrate precisely that this can be achieved at the required level. And it was an absolute success, because they actually demonstrated that they could do better by 2 or more orders of magnitude that the requirements that they had set before. So in that sense, the prospects for, given the excellent results that have been achieved on ground with LIGO, and then also the excellent results of this LISA Pathfinder, the prospects for LISA are very good. This might still take about a decade or so until it's launched and it starts functioning. And then there are, of course, longer term plans, some of them based on atom interferometry, others just on pure laser interferometry, to cover also the interesting frequency regime between the frequencies that are achievable by LIGO, which are in the order of between tens of hertz and kilohertz, and the millihertz range of LISA. There's also interesting physics and astrophysics in between, and that would require some other missions, complementary missions. And there are already some ideas, some plans for the longer term.
Okay, we have another question by Paul Ferreira regarding the first part of your talk about sending photonic quantum states to space. Did I understand correctly that you would like to investigate if gravitational redshifts are different for classical and quantum states of light? I was wondering why they should be different.
Well, no, actually, so that's a very good question, if that was not clear. So the expectation is that they would be equal, but it's, of course, still an interesting point to check that quantum states of light behave as we, in most cases, expect, similar to classical light. So the idea here is still pushing the limits and testing these effects or measuring these effects with, as I was saying, interferometers that have no classical analog. But indeed, the expectation from the standard standard quantum field theory in curved spacetime that combines general relativity with quantum field theory, the expectation is that the outcome of the measurement should be the same. If we find some difference, that's of course an interesting hint of some new physics that might even have a role in the marriage of gravitation and quantum mechanics, which still an open and very interesting field in theoretical physics.
So I myself have a question about the relation of quantum versus classical. So you spoke about gravity gradients that you need to mitigate. And I was wondering, is it sufficient to do this at the classical level? So just for the center of mass of your wave packet, or do you need to worry also about the shape of the wave packet being affected?
Yeah, that's an excellent question as well. So at the level that we are foreseeing in the near future, the main effect that I was referring to is for the central position of the wave packet. But in the very, very long term, you are right that that would also affect, it would mean that in this case, however, the effect would come from having not just the gravity gradient, but slightly different gravity. So gravity gradient, you can view it. Are you still seeing my slides?
No, we just see. So I don't know if it's possible to bring up the slides again?
Let me see if I can, maybe I can share again.
Yes, that's okay.
So if you look at this picture here, the central trajectory would, if you go to the freely falling frame, it's just co-moving with that trajectory. And then you see the tidal forces. And these tidal forces, of course, can lead to some slight deformation of your wave packet compared to absence of tidal forces. They basically just look like a, in this case, for example, an inverted harmonic oscillator. It's just at a very, very weak frequency of, inverse of period of thousands of seconds. So that lead to a very, very small change in the expansion of your wave packet. More importantly, if these gravity gradient, these tidal forces are similar for the two arms of the interferometer, that's an effect that will not, it will be the same for both arms and it would not affect your interferometric measurement. So, however, if you are in a situation where these tidal forces along the two arms of the interferometer are slightly different, and you look at the slightly different of these already small effect on the expansion of the wave packets, then that would become relevant. And that's something that it's it's an effect that, but it's still a number of orders of magnitude away that most of the planned measurements. But it's certainly a very interesting point, and at some point it will become relevant as well. So it's still a bit far from that. This method that I was mentioning here is focusing mostly on the central trajectories, which is what we expect in the near future at this level of 10 to minus 12, but even 10 to minus 15, 10 to minus 17, it would still be the dominant contribution. But yours is a very good point, and it certainly gives rise to an effect when you have differences in the tidal forces acting on the wave packet along the two arms. And it's something that is there if you push a little bit further these limits, absolutely.
Okay, thank you, Albert. So we have 3 more minutes, but I think we can give people a 3 more minute longer break. So let me close this session by thanking all 3 speakers, Emmanuel, Ivo, and Albert, for their really fascinating insights into quantum simulation, quantum metrology, and quantum technologies in space. And I look forward to seeing you in further sessions later in the conference. Thanks, everybody.